Hello and welcome once again to my channel. And actually, there is some problem. I think the sound will be quite lower today because the mic which I had that fell down and it got broken. So, so I will have to make this video in the open without the use of a mic. So the sound might be lower. Okay. So before moving on to the to our next topic of statistical physics, which is microstate, first of all just read these two things which are written on the board. Please quit watching TV news and reading Hindi newspapers. Okay. First of all, quit watching TV news and quit reading Hindi newspapers. Only read Indian Express and The Hindu. Okay. Okay, only read Indian Express and The Hindu, although that is also a censored news. Many of the news are censored in it. It is controlled by the government. But still it is important for the exam. So for 1 or 2 years, just read Indian Express and The Hindu. Do not read anything else. And do never watch this, okay? Just quit watching this. And quit this also. Okay? So, the second advice to all of you is that uninstall these financial scam apps. Okay, these are just financial scams. That is Rummy Circle, Ludo Pay, Zoopy, Ludo Supreme Gold. A lot of them are there. Pokerbazi.com. Okay, My 11 Circle. Just uninstall. Just uninstall these because these are financial scams and nothing else. No one can become, just note this thing in your notebook, no one can become rich with the help of gambling. Okay, no one can become rich with the help of gambling. So the microstate or the microscopic state, also called the quantum state of a system of particles, is specified by quoting the states such as position, momentum, orientation, and configuration of the individual particles. For a given macrostate, a system can have many possible microstates. Okay, so microstate, also called as the quantum state of a system of particles, is specified in such a way that when we code the position, momentum, orientation, configuration, etc. of the individual particles, okay, then it is called as the quantum state or microstate. So for a given macrostate, a system can have many possible microstates. I can give you one example over here. For example, when you used to write during the time of your JEE, okay, during your JEE preparation, once upon a time you must be preparing for JEE, right? You must have been preparing for JEE once upon a time. So at that particular time, you must have learnt all these things that uh, one s orbital is like this. You used to write the electronic configuration, okay, and the 2p orbital, okay, 2p orbital has done degeneracy equal to 3, right? 1 2 3 4 5 6. It can have maximum of 6 electrons. 2p, then 3d we have, right? So 5 orbitals will be there. 1 2 3 4 5. Okay, so 1 2 3 4 5 6 7 8 9 10. Okay, this is what is 3d. So at the time of JEE you had learnt all this. So all these are basically your microstates. Okay, this is microstate number 1, this is microstate number 2, this is microstate number 3. Okay, so corresponding to 2p, 2p is a macrostate. Okay, 2p is what? Macro. 3d is what? Macro. 1s is what? Macro. Over here in this macrostate there are two microstates. Two microstates. Over here there are 6 microstates. Okay, and over here there are 10 microstates, right? So you used to learn this at the time of JEE. The electronic configuration of elements you used to write like this. Similarly, you can do the same thing for nuclear configuration also. Okay, but some things will be different. But for electronic configuration, you had learnt like this. So there are like this, and then for you also have. Then what is this called? This is S. This is Px. This is Py. Right? This is Pz. Then this is what? Dxy, dyz, dzx, dx square minus y square, dz square. Did you get it? You used to learn all these things at the time of JEE once upon a time. Although if chemistry was not your subject, you have quit chemistry after 12th, suppose, then you might not be remembering all these things, but a blur idea of it you already have. Okay, so these are basically, this is what is meant by the microstate basically. Okay, so for a given macrostate, a system can have many possible microstates, right? So this is the thing. Now calculation of probabilities. Suppose we have n identifiable or distinguishable particles to be distributed in n cells, small n cells. Capital N number of particles to be distributed in small n cells. Now let us first understand the meaning of distinguishable and indistinguishable particles. It is important to learn this. For example, suppose I have two balls, two balls over here and two balls over here. Okay, everything is same for these two balls. Okay, this is also a smiley ball, this is also a smiley ball, this is also a smiley ball, and this is also a smiley ball, suppose. But the difference is that this is green in color, suppose this is green in color, this is blue in color. Okay, and these two are red in color, then these two are red in color. Okay, so these are basically your indistinguishable particles. Indistinguishable balls. Identical but indistinguishable balls. Okay, and these are identical. No, not but, and will come over here. Okay, identical and indistinguishable balls, and these are identical but distinguishable balls. Okay, these are also identical, these are also identical, but these are identical and distinguishable, the green one and the blue one. They are also identical, everything is same in them, size is same, shape is same, size is same, shape is same, everything is same, but the color is different. So they are also identical, but they are distinguishable. Distinguishable means they can be differentiated. And over here they are identical but indistinguishable. That means they cannot be differentiated. They cannot be differentiated. Okay. So this is the thing. Suppose we have an identical. Suppose we have an identifiable or distinguishable. Distinguishable means particles of this kind. Okay, particles of this kind. The first category, to be distributed among small n cells such that there are n1 particles in the first cell, n2 in the second, and so on and so forth. Okay, to find the number of ways in which this can be done, we begin with two containers. So suppose we have two containers with us. Suppose this is your container number 1 this is your container number 2, this is your container number 1, and this is your container number 2. Okay, so what happens is that when you try to distribute the N1 particles over here in this container, and when you try to distinguish these N2 particles over here in this container, and N2 particles in this container, and N1 particles in this container. So these are what? These are basically your containers are what? Macrostate. Your containers are what? Your macrostate. Containers are your macrostates. And the arrangement of these N1 particles among themselves inside this container, and arrangement of these N2 particles within themselves inside this container, all these are basically microstates. These are what? These are your microstates. Okay. So number of such meaningful distributions is given by this formula, which comes from the permutation and combination concept. So you have to just remember this formula, that suppose we begin with two containers, we have two containers. So suppose the particles are what? So particles are what? Distinguishable. Now what is the difference between distinguishable and indistinguishable? You will learn here. See, suppose this is your container number 1. Suppose this is what? This is position 1, this is position 2. This is position 1, this is position 2. So if I interchange this position, suppose I interchange this position, then what will happen? Number 2 will go here, number 1 will come here. So second unique this will be found. Okay, so blue ball will come over here and green ball will go over here, right? And in this one even if we interchange these two, okay, the same I will get, red and red. Okay, so these are not unique, these are repeated. So only one possible arrangement is there. In the case of indistinguishable, only one possible arrangement is there. And in case of indistinguishable, only one possible arrangement. And in case of distinguishable, two possible arrangements, right? So this is the thing. Now when you try to arrange these, so number of such meaningful distributions is given by, for these distinguishable particles, okay, for these distinguishable particles the number of such distributions in these two containers is given by the formula, as there are only two containers. So NCN1, you can either say NCN1 or you can either say NCN2. So the formula for combination, you know this. Okay, there are two type of n choose n1, n choose n2. We read it like this. You must have learnt in your permutation combination classes in 11th and 12th. This is read as ncn1, and this is read as ncn2. Okay, means n choose n1, n choose n2. So your total number of particles is capital N, which is equal to n1 plus n2, because you have considered only two containers. As you have considered only two containers and there are n1 particles of certain energy, okay, there are n1 particles of a particular energy. Okay, see over here, there are n1 particles in the first cell, n2 in the second, and so on. Okay, so like that. So the total number of possible ways will be n factorial divided by n1 factorial, n minus n1 factorial. This is the formula for your C function, means choose function, combination function. So n factorial divided by, now n1 plus n2 is your total number of particles, that is capital N. Okay, so n minus n1 will be equal to n2. Okay, so this is the thing. And your this also is n factorial divided by n2 factorial, n minus n2, n factorial divided by n1 factorial, n2 factorial. Okay, all these will be equal because there are only two containers and n1 plus n2 is equal to your capital N. So that's why this is the thing. As you note it down and you will study in the before coming to upcoming class, so you will understand this thing after revision. If after revision everything will be clear. So thus in general, the number of independent ways of distribution of n particles among n cells, small n cells, distribution of capital N particles among small n cells, such that n1 particles is in first, n2 in the second, and so on. So total number of ways will be n factorial divided by n1 factorial plus n2 factorial plus n3 means multiplied by, okay, like this. Suppose, let us consider this, let us understand this, what is the meaning of this. Suppose I have, energy level E1, okay, then I have energy level E2. This is non-degenerate. Non-degenerate means its degeneracy is equal to 1 because only one quantum state is there. Over here there are 1, 2, 3, 4, 5, 6, 7 quantum states. So it is 7-fold degenerate. Okay. And suppose I have one more energy level over here which is 3-fold degenerate. It is E3 and this is 3-fold degenerate. 3-fold degenerate. Okay. Suppose now let me draw it properly, okay? Let me draw it properly. 1, 2, 3, 4, 5, 6, 7, okay? Like this. Now I have n1 particles over here, suppose. n1 particles in this energy level, n2 particles in this energy level, and n3 particles in this energy level. Then what will be the, and suppose the particles are distinguishable, okay? Suppose the particles are distinguishable. So if they are distinguishable, then what will happen? So the formula can be written like this over here, that W, that is your W value, means total number of combinations possible, will be simply your n factorial. N factorial means your total number of particles, and capital N is equal to your n1 plus n2 means the total number of particles, n1 plus n2 plus n3, okay. So divided by what will be this, n1 factorial, n2 factorial, n3 factorial, okay. This is the formula, okay. So this is the formula, but this formula holds when all these are non-degenerate, okay. In this case degeneracy will also come into account, okay, but multiplied by degeneracy factor will be there because I have considered these to be 7-fold degenerate, etc. But suppose if they are non-degenerate, then what will happen? Suppose they are non-degenerate, all have only single quantum state, all of them have only single quantum state, okay, no degeneracy is there, just forget that they have degeneracy, okay, just forget this and write over there that they are also non-degenerate, means degeneracy is 1, non-degenerate. Then what will happen? This formula will hold good, n factorial divided by n1 factorial, n2 factorial, n3 factorial, okay. This is the number of ways in which distinguishable particles can be arranged, okay. So this is the thing. In general, this formula can be written like this. In general, this formula can be written like this. W is equal to number of microstates in the macrostate. Okay. Your W will be what? Number of microstates. It will be equal to number of microstates. It is very quite clear, quite obvious from here. So this is what your thermodynamic probability can be measured from here. Okay, so we will learn about thermodynamic probability and all those things, but in the next class. So it is the number of microstates in the macrostate. Okay, so thank you very much. So this is clearly equal to number of microstates, right? This is quite clear now, because suppose if there are n1 particles over here, suppose n1 is equal to suppose 2, n2 is equal to your suppose 4, and n3 is equal to suppose your 3. then what will happen? You will arrange 4 particles over here, you will arrange 3 particles over here. Okay, so these will have some arrangements within themselves, because this and this can interchange within themselves, this and this can interchange, this and this can interchange, this and this can interchange, then this and this can, this and this can, this and this can. Okay, so a lot of combinations are there. So all these arrangement within themselves, arrangement of this with this, 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 with this with this with this, all these will be your possible arrangements. So all these will be possible microstates. Okay, number of microstates in the macrostate, particular macrostate, how many microstates are there in a particular macrostate, this can show you. Okay, for a given combination of non-degenerate or energy levels. Okay, so only a single container is there. Non-degenerate means only a single container is there. Non-degenerate means only a single container. Non-degenerate means only a single container. But if they are degenerate, suppose there are two containers at the same energy level. What does it mean by degeneracy? Suppose there are three containers at the energy level E3. There are two containers at the energy level E2, and there is only one container at the energy level E1. Then E1 will be non-degenerate, E2 will be twofold degenerate, and E3 will be threefold degenerate. Okay, and suppose E4 energy level has two containers. E4 energy level has suppose two containers. So this will be twofold degenerate. Okay. So the number of containers means the energy of this, energy of this, and energy of this will be same. Energy of this, energy of this will be same. Energy of this, energy of this will be same. Okay. So these are basically your degenerator. So in this particular case, if we try to arrange the particles, that n1 particles are here, n2 particles are here, n3 particles are here, n4 particles are here, if we try to arrange like that, then we will find that this formula does not hold good. Then this formula will not hold then, because you have more than one container. Because you have more than one container, over here there are more than one container, there are more than one container, more than one. So this formula, that w is equal to n factorial divided by n1 factorial into n2 factorial into n3 factorial into n4 factorial, this formula will hold good only if such a condition is there. E1, E2, E3, E4 all have single container, means non-degenerate. Okay, so in this case only this formula will hold good, that it will be equal to n factorial divided by n1 factorial into n2 factorial into n3 factorial into n4 factorial. Okay, and this can be represented in general as, suppose there are n cells, 1 2 3 4, there are n small n energy levels. So what will happen? Over here there are n1 particles, over here there are n2, over here there are n3, and so on and so forth. Over here there are n small n. Okay, over here there are n small n particles. Okay, so all these things will be product I equal to 1 to small n, and this will be equal to ni factorial. Okay, so this is the thing. So hopefully you got the idea of microstates. Hopefully you got the idea of microstates. So thank you very much. If you haven't subscribed to our channel, then please do subscribe to it.